So let's get started on chapter 5, everyone. So this is 5.1, solving systems of linear equations. I went ahead and wrote down or copied over the initial part of the note. So go ahead and copy this down or pause to copy this down. And I'll explain it as we go here. And then we'll do examples together. So first, we want to look at two equations and two unknown variables. So what that means is, and the key here is in 5.1 is solving systems of linear equations. Now linear, the root word there is line. So it's linear equations and two variables. So you get these lines. So if you have a line, just keep in mind, actually I wrote this down here, every point on the line, let's do a highlight like orange or pink. Every point on the line is a solution to the equation. That's what the line means. A line represents all the solutions to the equation. So that's when you do like that T-chart or something, that's what you get. So if you look at L1 here and then L2 here, then every point on the line here and here represent solutions to the equation. So that when you look at what we call a system, so the the system of equations is asking for what point, basically what ordered pair x, y would satisfy both equations. So clearly in the middle here, right, let me point to it, in the middle here, that point satisfies both equations. So for two lines, basically to have what we say a unique solution to the system, you must have two equations. So we call that two equations, two unknowns, two unknown variables. The other possibilities are here. You could have two lines like this that are parallel, in which case there's no intersection, so we would say no solution. Now it's also possible to have two equations, two separate equations that look different, but they represent the same exact line. Let's see, down here I made one up. So right here are two equations. They of course are different, but you can see, what did I just multiply by? I multiplied by 2, right? On both sides. And it represents exactly the same line. So that's this case. So it's the same line. So what we have then is some terminology that we talk about. So you have what we say is the system. We say the system in the first and last case are consistent. So a system, here's a definition. So a system is consistent if it has at least one solution. So consistent, at least one solution. Okay, so that's of course case 1, let's call it 1, 2, and 3. So case 1 and 3 are consistent systems, we say. Then we talk about the equations themselves. Are the equations independent or are the equations dependent? And so what that basically means is this idea over here that you can create one equation out of the other, and it represents the same solutions. Those are what we call dependent equations. So the definition, which is here, the equations are equivalent if they have the same solutions. Okay, so let's look at some examples of that. So we want to talk, so we're going to be solving these systems, and we're going to do a couple different steps, and we'll go into solving systems of 3 equations and 3 unknowns. We won't get to that on this video, but that's where we're heading. So let's look at a couple examples how to solve the system, because that's our goal. So for example, let's move that up. You might be asked to solve 3x minus 4y equal to 5 and x minus 3y equal to 6. So there's a couple methods to use, and first method I want to show you is the direct substitution. This is kind of like the no frills, just go for it, brute force method that you always want to have in your back pocket if you needed. And this is called, so that's the substitution. So substitution method, what you do is you isolate one variable in one equation. Okay, so let's do that. So you take one equation, we will, or can, label this equation 1 and equation 2. We will use that later for other things we do. So isolating one variable, so let's just take equation, looks like equation 2 looks easiest to do. So take equation 2, which is x minus 3y equal to 6, and then let's solve that. So the easiest way to solve that, as you can see, is just add the 3y on both sides. So add 3y and you get x is equal to 3y plus 6. Once you do that, you substitute back into the other equation, whichever one you didn't use in the first place. So it would be equation 1 in this case. So you take the 3x plus 6 and substitute it for your x in equation 1, and then solve for y. So it's 3, and then instead of x, so this is equation 1. So it's 3, and then x is actually 3y plus 6 minus 4y equal to 5. And then you solve for that variable. Whichever variable is there at this point. In this case, it's y. All right, so let's do that. Multiply through, you get 9y plus 18 minus 4y equal to 5. Continue to solve, collect like terms, and you get 5y equal to negative 13. So y is equal to negative 13 over 5. So from there, what you would do is we say back substitute into either equation, well, I'll write it like that, either equation 1 or equation 2. So you take either one of those and substitute what you've solved for that particular variable. So we take this negative 13 fifths and substitute back into either equation 1 or equation 2, and then solve for x. I always pick the simplest one, and which looks like it's equation 2. So you get x minus 3 times y, which is negative 13 fifths, equal to 6. Okay, so x, and you'll get a plus 39 fifths equal to 6. So x is equal to 6 minus 39 fifths. So it's 6 times 5 over 5 minus 39 fifths. So that's 30 minus 39 over 5. So that's negative 9 fifths. It's had a lot of fractions in it, didn't it? So your two solutions then are, your solution is, it's an ordered pair. That's kind of the key here. Your ordered pair solution is the negative 9 fifths and your negative 13 fifths. And then you write it in a solution set in an ordered pair, because remember, it's the point that's the solution to the system. And then we say, so it has what we call this, so this is a unique solution. This is a unique solution. We say the system is, and then is it consistent or inconsistent? So a system is consistent. Where's the definition here? A system is consistent if it has at least one solution. So does this have a solution? Yes. So the system is consistent and the equations, are they dependent or independent? So do they have the same solutions? No, they're not the same solutions. So we'll get to that later. That's only when you have the same line or an infinite number of solutions. We'll talk about that a bit later. The system is consistent and the equations are independent. So the book will ask some of those questions you may want to take a look at. Let's do elimination or addition method. That's kind of what we're heading. You need to know this, solve and substitute for just in general for other types of systems. But for systems of two equations, two unknowns, you're really going to use more like elimination. So let's look at this example. Okay, so solve. Now this one, I wrote it out a little different well, the book, I picked one, I should say, so that you can see what you have to do first on this. That's the first equation. Second equation is 2x plus 2 equal to 7y. And so what you want to do first is write in standard form. So standard form is always ax plus by equal to c, where a, b, and c are constants. So you got to distribute that, right? So maybe try that. Stop and put that in standard form, both equations. Okay, so both equations in standard form. It may take 2 steps. Negative 3x plus 12 equal to y minus 4. So then you bring everything over. We'll do this step by step. So 2x minus 7y equal to negative 2. But this one, the top one's not standard form. So let's do that again. Negative 3x minus y. And then it's equal to the constant. Where was I? I had another y in there. I'm missing something. That was positive 12, y minus 4, negative 3x, or maybe not. Oh, I know what I messed up on. This was supposed to be a y. Okay, I'm not going to edit this video. You're just going to keep going. That was a y in there, so it's negative 3y. So negative 3, and then that's a positive 3y. There we go. And then when you solve it, let's just fix this over here. You get plus 3y. Okay, then you get plus 2y equal to negative 14. Oh, that was a 14, so I had made a couple mistakes here. Okay, so that's fixed. Now, my original equation was wrong back up in here. So negative 3, okay, so that looks right. Otherwise, it messes up the rest of my stuff. And we may not get a unique solution of what I wanted to look at. Okay, now we're rolling. So 2x minus 7y equal to negative 2. Okay, so this is what we call solve, sorry about that, by elimination. The book might call it addition, because we're going to be adding the equations together. So this is standard form, and we're going to call this equation 1 and equation 2. So what we want to do is basically multiply by a constant and add to eliminate one variable. So we can see that if we did 2 times equation 1 and 3 times equation 2, you would have negative 6x plus 4y equal to negative 28, and then 6x minus 21y equal to negative 6. So by doing that, that step, you can see that if you add those two equations together, so now you want to add them, you will eliminate x. So by adding, these two will be gone. That's 0. So what you get then is, so you add them, so you do, so just say add, you get negative 17y equal to negative 34. And then divide those, and what do you get? You get y is equal to 2. So then, same as before, back substitute into equation 1 or equation 2. And you can actually go back to this either one of these, this one. It doesn't matter. Okay. So let's see, what did I pick? I picked the second equation again, looked a little easier. So I picked equation 2, this one right, yeah, so right here. So I picked equation 2 to do my back substitution. So that's going to be 2x minus 7 times y, which is 2, equal to negative 2. And then I solve that. Okay, so then now you just want to solve that. So maybe take a moment to solve that, get your x. Okay, so you get 2x minus 14 is equal to negative 2. Keep going. 2x is equal to positive 12. So x is equal to 6. So your solution then, you get a unique solution, just like before, which is 6, and so that's your x, and then your y is 2. So 6, 2 is your solution. So what we say then, if you have a unique solution like this, you say the system is consistent and the equations are independent. All right, so try this example. I'll give you another example, and I'll maybe wait to work it out or just show you later what happens. So suppose you have 3x minus y is equal to 2 and negative 9x plus 3y is equal to 4. So solve that by elimination. Okay, so solve that by elimination, multiply and add and see what you get. So this one's a little different than what we just did. It is not a unique solution, and we'll cover that in the next video when we go on. So next video we go on to